Thank you all for being here. I'm very excited to talk to you guys and introduce to you Radical AI. As mentioned, I'm one of the founders of the company. We've been working on Radical now for about 2 years. The entire company is based here in New York City. And what we are trying to do is effectively fundamentally rethink the way we approach physical sciences, starting with material science. And that rethinking is one that is rooted in autonomy as well as in machine learning and the combination and bringing together of those two things. So why materials? The reason we started with materials is because materials are in everything. Everything you can think of that is around you, the chairs you're sitting on today, the water bottles that you were drinking out of at some point in the afternoon, the computers and cell phones that sit in our pockets and backpacks, all of these things come from innovations in materials. And truly, we can actually think of it not just as materials are in everything, but materials are everything. Semiconductors, lithium-ion batteries, solar energy, jet engines and turbines, automotive innovations, rockets, all of these things at the end of the day, at some point, were being prevented and blocked because we didn't have access to a specific material that allowed the technology to develop. And so the idea always came first. We always had an idea for what we wanted to do with technology, and it was the atoms that followed afterwards. And those atoms oftentimes come very, very slowly. And so the question that this talk is centralized around is, why is material science so slow? And is there anything we can do to speed it up? Material science and really all physical sciences have not really adapted over the last hundreds of years. We continue to do things in a way that is entirely serial, it is entirely human driven, and it is one that is incredibly slow because of those things. What we have at Radical is something that is entirely different, and it is one that is based off of a closed loop approach to science. And so what we do at Radical is we use machine learning to come up with new experiments. We run them with robotics inside of a self-driving lab. Those instruments will read the data and send them back up to our data lakes where our machine learning programs can update, understand their thinking, their wherewithal for what the world looks like, and improve the next iteration of an experiment. That is what we mean when we talk about a closed loop approach towards physical sciences that is rooted in autonomy and in intelligence. And there are a lot of companies in this space, as was mentioned, but we think we are the only company that is focused on building every single component in this flywheel. And that is important to us because if you don't build all of the components, you don't have a closed loop approach. And without the closed loop approach, you will never create a flywheel. So that is what we're doing here at Radical. Before we go into some examples of how we do this, I wanted to present an overview of what I mean when I talk about a self-driving lab. So I have this video here that is footage from our lab here in Manhattan, just to give you an insight of what it looks like to run experiments at Radical AI. So all of the equipment that you're going to see throughout this entire video is stuff that sits here in our lab in Manhattan, and it's all equipment, software, hardware, mechatronics, robotics, all of it built entirely by the Radical AI team, and all of it working together in unison to solve very specific and complex material science challenges. You can see that we do the full synthesis and characterization as well as downstream testing, in addition to, of course, the designing of individual experiments that will make their way through this loop. So now I want to walk through a few examples of what this actually looks like at a more specific level. So to start, I want to point you to this tool right here. It looks incredibly archaic because it is archaic. The design for this tool hasn't changed in decades. It's known as a vacuum arc melt reactor. And this is how you actually synthesize alloys. It is a machine that is literally described by the maker of it as lightning in a box. It is a plasma torch that will blast different precursor elements at 3,500 degrees Celsius in order to create a melted alloy. We have automated this tool. And as you can imagine, automating this is perhaps one of the most extreme places you can apply robotics and perception to. You have an area, an environment in which the plasma occludes the stage. You have an area and an environment in which the conditions and the oxidative properties of it mess with the equipment. You have something that is incredibly challenging to take on, not just from a mechanical mechatronics perspective, but also from a computer vision perspective. And we tried foundation models on this. Our team attempted SAM2 and others, and they completely failed. They did not live up to the task at all, even with fine-tuning and post-training after the fact. So what we did instead is we actually created our own perception pipeline that was tailor-made for this specific case. And there's some details there on how we did it, but the overall high level of it is that we were able to create a pipeline that was 80 times faster than the leading foundation model, and at the same time provided dramatic increases in accuracy. Again, I have a video that can actually show you what this looks like in action. So what you'll see here is an actual arc melt process going on and our computer vision pipeline on top of it. The green area represents elements that have not melted yet. The yellow area represents sections of the crucible in which we are semi-melted. And eventually you'll see red areas where we have a full homogeneous melt. Again, think about this. This is happening at 3,500 degrees Celsius. At its peak, the actual tip of the plasma torch is as hot as the sun. And yet we're able to dramatically and immediately learn in real time from what is happening and control the torch in order to create a homogeneous melt, which you'll see start to form right now. Again, all of this was built in-house by our team, everything from the hardware up to the software and every layer in between. The next example that I wanted to walk you through is really on the other end of the spectrum. We really showed you what it looks like to automate a specific piece of equipment so that it can drive throughput as well as data collection. But there's another aspect of science which is very core. What do we do next? What kind of hypotheses and ideas should we be running in a lab? And traditionally, when you are designing experiments, you would use Bayesian optimization for this. It's a trusted process. It's very often seen in drug discovery. But materials is an open formulation problem. And Gaussian processes, which is typically how you would do Bayesian optimization, don't really work well on open formulation sets. And so we can't just simply come up with a Gaussian process and optimize an acquisition function. We have to do something different. And so what we did instead is we actually approached the design of experiments problems with agents in mind. And so instead of fitting a surrogate model, what we have created is instead an actor-critic loop where we rely on an LLM to come up with new designs of experiments based off of a set of optimization targets as well as constraints, and a second LLM which acts as a critic or judge to that LLM. Those two LLMs have access to different tools, and critically, the design agent or the actor agent has access to over 1,000 synthesized experiments that ran in our lab. And those experiments are incredibly important because we can throw them into the context window of that agent, and it can have an understanding about what it previously did, how that resulted in good or bad results, and what it should be doing next. Again, this is what we talk about when we talk about building a closed loop. You have an agent that come up with new experiments, and those experiments are in part based off of both the software tools that we've created in-house, as well as the results of experiments that we ran in our own facilities in an automated high-throughput fashion. And you may be thinking, what does this actually look like in the real world? Well, there are two versions of the answer. Number one, you will see Slack messages like this, which popped up in our Slack channels just a few weeks ago. What happened at 4 a.m.? The agent decided to run an experiment. And so again, think about this. This is literally our entire team at home sleeping. And our agent decided it was a good time to run an experiment. So it queued one up, sent it down into the lab, and the lab took over and started working on it. That is the rethinking of science that we were talking about. It is 24/7 and it is actively learning. It is, as Keithan on our team describes, the autonomous lab dream. The results is the other way to talk about this. Well, at the end of the day, how do these agents do? And how do they perform against humans? The answer is very directly, they crush humans. They do so much better than our own human scientists can do on a variety of different tasks. So what you can see here is a multi-objective optimization where we are optimizing across hardness, So how hard is the material? When I smack it with a diamond tip tool, what happens? Does it shatter? Does it crack? Does it break? As well as oxidation. What happens when I put it into an environment that simulates high oxidative conditions? Does it crumble? Does it form a thin oxide layer? Optimize it against those two properties, we can see that agents dramatically outperform humans. They're able to, by almost a third, improve mean hardness, and they're able to improve oxidation protection by over 25%. The more obvious way to look at it is just to look at the top right corner of the chart. As you can see, the blue dots, which are our agent-driven experiments, are overwhelmingly dominant in the upper quadrant, whereas our human-based experiments in orange are barely noticeable. Our agents do outperform humans. And they do so over time as well. And the context that we provide those agents is a big part of the reason why. Again, you can see in this chart here that in the very beginning, when we don't provide any sort of context, any previous experimental results to our agent, effectively zero-shotting its way into a new experiment, it's not really able to understand or reason about what a good experiment could look like. And so it's all over the place. And then as soon as we provide experimental context into the agent, which is on the right side of that dotted line, you can dramatically see that it starts to converge on an optimal experiment. This is on single optimization across oxidation, but we've seen it across up to 5, 6, 7 target property optimizations as well, the kind of space where it becomes almost impossible for a human to optimize against. And this happens temporally as well. We have seen that hypervolume improvements do span across campaigns for our agents. So again, you can see that campaign 1, which is the first box, all the way down through to campaign 4. By the 4th campaign, we have seen that the learnings for the 1st, 2nd, and 3rd campaign are translating over so that our agent is more quickly able to get to an optimal solution faster. There are just simply more experiments that are likely to be or are closer to the target zone than they were in the earlier campaigns. And so all of this is why we think our approach, a closed loop, autonomy, and machine learning based approach to science, is the future of the physical sciences and truly the future of R&D. We think that it is the kind of thing that will dramatically change the timeline at which we come up with new discoveries. And so the question that I wanted to leave all of you with now in the last minute of this talk is what actually happens when we take a process that typically takes us decades, the R&D process for a new material discovery, and compress it down to 6 months. What all of a sudden is no longer impossible? Carbon capture at an industrial scale. Being able to power a safe and sustainable electric grid that is backed by nuclear fusion. Being able to come up with batteries that have the power density to power aviation, electrified aviation, even materials that we don't have a name for because we have no idea how to go out and find them. Those are the kinds of things that we think will become available once this closed loop approach using autonomy and machine learning to change the way we do science. We think those things will be there. And that is the vision for what we are trying to do at Radical. Thank you, everyone. I hope you enjoyed.